I think maybe we should get started. People joining later can watch our live streaming later on YouTube. Okay, so everybody, hello. Let's get started. Welcome to our Students as System panel session. So in this panel, we will discuss several topics regarding female researchers in the system area. So this is how our panel will look like. The first 5 minutes will be the introductions, like what is Students as System, who are the panelists, and some brief introductions of our panelists today. Then we will move on to the interview topics, which we collected during the past few weeks, and this section will be 30 minutes discussion. And then we will move to our audience's questions. In this panel, we have many audiences registered. It's not quite easy to coordinate with these many audiences across different streaming platforms. So this is to our audience. Instead of asking questions in Zooms, please post your questions on this online Q&A board and also vote for those questions that you find interesting. The link is shown here, or you can also go to our Students as System main webpage and find this Q&A board. We will go through the question list during this Q&A session and answer as many questions as we can. So before we get started, allow me to introduce a little bit about our organization. So Students as System, this is a student-run organization which we started at February of this year. We now have 8 students from 5 different universities. And our focus here is to help with other students in the computer system community. And we also want to provide information and also inspire future leaders in this field. And we're always looking for new members to join us, to work with us and organize future events. If you're interested, you may check our website on how to join. So in the past, we have organized many interesting sessions. We have hosted a panel session 3 months ago, talking about how to get started with computer system research as a new graduate student. And last month, we have also hosted a session on getting a job in academia. We're starting this new series of interviews about women in system research, and we have several speakers lined up. So if you have any suggestions or recommendations on the speakers, please feel free to contact us as well. This is pretty much about our organization. Now we will move on to our panelist introduction. So we're very honored to invite our first guest, Professor Christina De Limanchu. She's an assistant professor in the ECE department at Cornell University. She's well known for her work on data center performance and resource management. She has received many awards and fellowships, including Sloan Faculty Research Awards, 2 Google Faculty Research Awards, a Microsoft Research Faculty Fellowship, and many others. Her works has also received IEEE Micro Topics Awards 5 times, 1 topic honorable mention, and several best paper awards. Now we will give the stage to Christina. And Christina, could you introduce a little bit more about yourself?
Sure. Thank you, first of all, for having me and for organizing this. So, like you said, I'm a professor at Cornell. I recently moved to MIT. I work on computer architecture and computer systems. Specifically, a lot of the problems that we look at have to do with large-scale data centers and cloud computing. And the problems that we look at kind of span the system stack. So some of them are more on the hardware side, which have to do with how to build servers that populate data centers, what is the potential for acceleration that cloud applications might have. Some of them are at the middleware level, which is how do you schedule applications, how do you manage resources, and some of them are at the application level, which is what are the right programming frameworks to write data center applications, what are the right ways to structure data center applications, and some of that extends beyond data centers to IoT devices as well. So I'm at MIT now. I was at Cornell before. Before that, I did my PhD at Stanford and master's at Stanford, and I did my undergrad in Greece, in Athens. So I have a little bit of a double background, both of the European system and the US academy.
Wow, that sounds like a lot of experience. It's very impressive that your research seems to span the whole stack, and would love to hear more. Thanks for the self-introduction. Let's move forward first. So before we really get started, we also have a few organization members working behind the scene. We have from UCSD working on streaming and recording, Yue from Cornell prepared the slides, and we have Jay from Rochester working on the Zoom moderation. We also have Sahan as a backup session host in case we had any network issues and cannot have host the session. Sahan recently got his PhD from Virginia and will soon join Waterloo as an assistant professor. So thank you all for the student and system members and our panelists for making this whole thing happening. So next, we will move on to curated questions. We have collected questions during the past few weeks and categorized them into several topics. Each topic has a few questions. I will go through each questions and then hand it over to Christina. Okay, so the first topic, which is what I think that come up very often, is why do you choose your specific research topic? I mean, we know you're an expert in cloud computing and you did a lot of contribution during your PhD data center management, and later in Cornell, you specialized in microservices. But it seems like that, especially for females, there aren't many female researchers are working on these topics. So could you tell us a little bit more about how you identified your passion for this area?
Sure. So I started working on cloud computing in my PhD. So this was early 2010s. And that was about the time when cloud computing started becoming very prevalent, very prominent. Mm-hmm. The interesting thing about cloud computing is, at least at the time, wasn't so much the way systems were built, it was the scale. And it was the first time, minus high performance computing, where such large scale systems were as widely used. And they were very widely used by people that weren't necessarily, I mean, the end user, weren't necessarily experts in how large scale systems were built. Again, I'm talking about the end user, not the people building the systems. Mm-hmm. So that is what made that specific problem very interesting, that you used a lot of commodity equipment, but you use it at such a scale that traditional solutions didn't really apply. And that is what motivated a lot of the work that I did for my PhD, which was applying machine learning approaches to systems problems. At the time, this was more for scheduling and resource management problems, where the idea was, without knowing a lot about a new application, when you see a new application arriving in the system, how do you figure out where you should run it, how many resources you should allocate to it, what other applications might play well with it, so might not hurt its performance, and so on. And that was a good fit for applying ML to systems. Since then, we've extended this to other types of systems problems as well, whether they are hardware or software, but that is what started it. And what you have there in terms of collaborations between academia and industry. So cloud computing is one of the areas where this kind of collaboration is very important, because as academics, we don't have access to systems with hundreds of thousands of machines. There is a lot that you can do with smaller scale systems and the right applications. And there's a lot of great work in the community on building the right applications from many different universities. We've also contributed in that area, but collaboration is very important. So there's a few different ways that you can do that. A lot of companies have programs. For example, you mentioned a couple of awards. These are programs that initiate collaborations between academia and industry. Internships are a very good way. So for those of you that are students in the systems area, if you're interested in cloud computing and data centers, internships are a very good way to see what real systems look like, what are the problems that they run into, get some motivating data. And even if you cannot write a paper where the evaluation is, let's say, on Facebook or Google systems, just getting the motivation data from a large scale system is very helpful. So a lot of the work that we have done, both for my PhD and in my group now, comes from collaborations between academia and industry.
Yeah, so how do I I think that is very helpful suggestions. So how do you think, like, how much of your work is actually motivated by some real world problems, or are they just problems you read from the papers and then actually evaluate in the industry, or is it the other way around?
It's mostly the other way around. So it's mostly collaborating with industry to see what the problems are, and then the actual solution. Sometimes it's evaluated in industry, sometimes it's evaluated in our own systems in the university. And one benefit that academia has is you can try much more risky, so high risk, high return solutions, which are not always easy to port in industry. And the reason for that is because at the end of the day, they operate a company, they cannot make very radical changes that might hurt the performance or the efficiency or whatever metric they care about. And that is one advantage that academia has. You can try things that are very different, and if they work well, then you can take them and apply them in industry. The other way around is a little bit harder.
I see. That's interesting. So what do you think are some of the risky solutions that the industries it would be difficult to try? Like, what are the key challenges and open questions in this area?
Right. So yeah, I can tell you about that first. So cloud computing is not the newest field of research. It's been around for about 15 years at this point. The reason why it stays relevant and interesting is because over the past few years, there's been very significant changes in the way data center hardware is built and in the way data center software is built. So if you look at the hardware side, for a long time, cloud data centers were built with commodity equipment. So this would be basically very similar to a machine you could have as a desktop machine, just with more resources and then hundreds of thousands of this. But the actual machine was very similar to what you could go from Intel or AMD or ARM and buy. What has changed over the past few years is that there's a lot more specialization. And there's several reasons for that. The primary one is the end of Moore's law, which, if you've taken a computer architecture class, I'm sure you've heard of. And the result of the end of Moore's law is you cannot get better performance without increasing the power dissipation of the system. So the result of that is that you have to look for more specialized solutions that give you better performance at better power efficiency, or at least at the same power efficiency. Now, the disadvantage of that is that data centers used to be entirely homogeneous, and that's not the case anymore. There's a lot more hardware heterogeneity and a lot more hardware accelerators, a lot more specialization, and that complicates the management of the system. So that is one of the reasons why there's a lot of new research challenges on the hardware side of data centers. And on the software side, you have a similar story, which is that if you go 10 years back and see what cloud applications looked like, they looked like one gigantic code base that implemented, let's say, web search. And the bigger the application gets, that monolithic design approach doesn't really work or doesn't really scale because it gets very complex. So people have started using much more fine-grained modular designs for how they build their applications. And that is what you mentioned before, the idea of microservices or serverless compute. Right. So that's another reason why there's a lot of interesting questions right now in data centers on the software side, because these new programming frameworks, I'm trying to not get too technical, but these new programming frameworks create challenges with respect to scheduling and resource management, debugging, programming framework design, application design. So that is what has kept cloud computing very interesting as the years go by.
Yes, that is very true. As we have more and more different hardwares and more diverse applications and workloads, the whole resource management and scheduling thing becomes more complicated, but also more interesting. Okay. Yeah, thank you very much. So I think we don't have more time for this question. We should move to the next one. So our second topic is about keep motivated in the minority group. This topic includes many interesting questions, but again, we probably don't have enough time to answer all of them within this 1 hour panel, but we prepared several frequently asked questions for our panelists. So our first question is, being a researcher in an underrepresented group, have you faced any specific challenges?
Right, that's a good question. So I must admit that I've been very lucky in my mentors, both male and female, that I have not faced very serious challenges. Of course, there's cases where somebody might, make a comment that's not entirely appropriate, but I haven't seen something that's, very serious. I know there's a lot in the community that have, and if you haven't read an article by Catherine McKinley on, the issues that she ran into as a young assistant professor, I think that's when she started discussing it. And moving later in her career, that's a very interesting article. It's on the Cigars blog. I recommend that you take a look at it. So I don't have similar stories. Again, I've been very lucky both with my undergraduate supervisor, my PhD advisor, and the people that I work with as a professor as well, that I haven't run into significant challenges. One of the challenges is that you don't always have people with a similar background as you that you can discuss whatever it might be. It doesn't necessarily have to be work issues, any issue that you might run into. So that is one thing that comes up being from a minority group. But again, when I was a student at Stanford and in my undergrad, there were other female students that we had a group. We were studying together, preparing for exams and so on together, or discussing research questions. So that was very helpful. And that's something that I recommend in general. It doesn't have to be just female students. It's good to have a diverse group of people in your circle, but that's something that helps.
Yes. I am also aware that there has been a lot of this kind of underrepresented groups that organized by the officials or not unofficially. But people has been doing that for a while, and the circumstances has been improved. Well, there is still some things would need to be fixed, but I think we're getting better.
Mm-hmm.
So the second question is, what do you think is the secret sauce of being successful in system research?
Right. So I think, as with all research, the main thing is picking the right problems. So is what I was saying before about the difference between academia and industry. In academia, you can try much more radical approaches compared to what you can do in industry. Another advantage of academia is you can look further out in the future. So you don't want to be solving a problem that industry can solve in 6 months or a year. You want to be looking at what are the big problems 5 years, about 5 years down the line. You don't want to go too far because then it's a bit unrealistic. People won't care. But 3 to 5 years is where you want to look. That's the main thing. The main thing is picking the right problems. That's where collaborations help. Collaborations with industry, because they operate, at least in my area, they operate large-scale systems and they see the data, they see what the problems are, but also collaborations with academia. It doesn't just have to be with industry. And many times if you talk with people that are a little bit outside your area, they might notice things that because you're in it, you don't necessarily see. So even if they're not versed in the details of your work, they might see some high level or low hanging fruit that you didn't necessarily see. And that is a good approach to solving a problem. So that helps as well.
I see. That's interesting. So one of the most helpful ways for finding an interesting problem is to actually talk to people not really working in this area, but maybe in an area close to this area, and they may see something that we don't see.
Right.
So, who do you think people have? Like in the past? Who do you think that inspired you most during your career?
Right, that's a good question. I'm not going to attempt to enumerate people because I'm sure I'll forget some. There's many. If you've been to any conference recently in architecture or systems, thankfully these people are starting to get recognized with awards, especially from underrepresented minorities. So that's great. I'm sure those are some. Catherine McKinley that I mentioned before, she's done great work, both great technical work and great work in encouraging people from underrepresented groups to join computer systems and computer architecture research. But again, I don't want to give a list, but I will say again, my graduate supervisor, he was great. He was great also because not being in the US university system as an undergrad makes it a little bit harder to apply. So it makes it harder to know what to be careful when you're applying, what to pay more attention to, which universities are the right ones, how do you pick the professors that you want to work with. So he was great helping with that. And then my PhD advisor, Chris Koziraki, is also great, both in encouraging me to find a topic that I'm interested in, even if it wasn't exactly what he was working on, because a lot of my PhD work had a lot of mathematical foundations, and that wasn't necessarily his favorite thing, but he was great at encouraging me to work on that. So these are the kind of people that are very helpful to have in your career.
It sounds very nice. Yeah, so it's nice that these people are nice and helpful. So, but I'm just curious. I know you talked about how you see cloud computing can really change the model of computing and how people use the resources. But I'm just curious, is there like one or two people that actually inspired you to enter this field, or you just started by yourself?
So enter the field, I would say enter the field of computer architecture, because once I got into computer architecture, then finding the more specific topic, that kind of sorted itself out. But again, I would say my supervisor, so the professor that was teaching the computer architecture class in my undergraduate, it was interesting because part of the class, so first of all, we were using the Hennessy and Patterson book, and they were using a very similar structure for the class to the one that were used at Berkeley and Stanford. So I got an idea of how classes are taught in a US university, which up until that point, I didn't know. We were using mostly books from Greece, which, the content was similar, but the way of delivering the class was different. So that helped a lot. There were specific ideas in computer architecture that I really liked, like pipelining, memory hierarchies, advanced processors. Those were some of the reasons why I went into that field. And then from there on, I found the idea of addressing problems at a very large scale interesting. And thankfully, that was about the time that cloud computing became more popular. So it kind of merged. But I think it was a little bit of a happy coincidence too.
Everything sounds just about right. The timing was right, and the textbook you were using was right. Thanks for this. For those we now have so many great researchers produced by you. Okay, so I think we need to move to our next topic. Our next topic is about future. With that, we have the following questions for our panelists. So the first question is, how would you promote the DI in the system? I know this is a topic you must have been asked pretty frequently, but still we want to hear about the answer.
I think the best way is finding the people from underrepresented minorities, and a lot of it is women, a lot of it is other minorities as well, that are interested in the field. And in order to be interested, you need to know what the field is, and the earlier in the education system you get to learn what the field is, the better. So some ways to do that are through high school and even middle school programs. So at Cornell, for example, they have a lot of summer schools, and at MIT as well. They have a lot of summer schools where they'll bring in kids from grade school, kids from middle school, kids from high school, and they'll have them do a couple weeks school where they see some aspect of engineering or computer science. They'll do some project. And for many of these kids, they have not seen this area in the past, so they don't even know what are the options in engineering or computer science. And if you look at the statistics, many of those students end up following an engineering or computer science degree. And again, in many cases, it's not that they wouldn't follow it because they weren't good at it, it's because they never had the opportunity to see what it entails. So that is what helps the most. I'm less worried about, there's a lot of discussion about the ratios of female to male students being 50-50 or whatever. I'm a little bit less worried about that, and a little bit more worried about everybody that wants to have a career in STEM in general, or CS or E, and has the ability to do that, to have the opportunity to do it. Whether that ends up in a ratio of 50-50, 60-40, or 40-60, I care less about, but I care more about the people that want to do it and have some talent in it to be able to do it.
Yes, so the takeaway is people who really want to do research should get the opportunity to do that, no matter what's their specific circumstances is, right?
I think there's a lot of it comes down to the universities providing this opportunity, or even schools providing this opportunity. So you can't always put the burden on the student to find that opportunity, especially when they come from underprivileged backgrounds. So that's one place where universities help with this. You know, summer schools are one example. There's others similar as well.
Yes, thank you. So, and do you have I know you just said like universities should be the one that actually provide this kind of opportunities, but on the current situation, current environment, do you have any specific suggestion to female researchers, like how to identify their unique strengths and how to find opportunities based on the current way it is?
Right. And I assume you're saying once you are an undergraduate student, right?
Yes.
Right. So as an undergraduate student, one advantage that you have is you have to take classes from many different domains. And that's something that I encourage people to do. So don't try to over-specialize very early. For example, at Cornell, you have to supervise some first-year students, and I see a lot of them want to immediately pick a major, pick a direction within the major, and then only take classes from that area. And I think that's a mistake. You have the opportunity to take so many diverse classes, at least in the first couple of years. And that's what helps you identify what you actually like. For example, when I went into my undergrad, I liked math and physics. If I only took math and physics classes, I would never have seen computer architecture and systems, and I would never have followed that area. So I think that helps. Try to be as diverse as possible in the beginning. And then once you identify some topics, some areas that you like, approach the professors about doing even a short-term project, research project with them. Because that will also tell you if you really like the area, but also if you really like research. And it will tell you that early enough that you can then maybe prepare a paper, or at least, have a long-term collaboration, and all that helps when you apply for grad school.
Yeah, I think that is a very good suggestion, but I know that, and even for myself, when I just entered college, I find something interesting, but I didn't know, like, if I approach a professor, ask for an opportunity to do research, I don't know how much I can contribute. So what do you think are the professors' expectations for those young students?
That's a good question. So, professors know that undergraduate students are very busy. We don't expect huge contributions. There are some students that either they're not taking a lot of classes, or they really like the project, or I don't know, they don't sleep, and they make fantastic contributions, much more than we expect, but that's not the bar. The bar is, these research projects are for the students to learn about the area. We don't expect a paper to come out of it, or we don't expect a huge contribution out of it. The contribution is not for the group so much as it is for the student to see if they like the area and if they like research. So I don't think students need to be worried that much that they might not have enough time, or they might not make as many contributions as a graduate student who's 100% time is devoted to research. Of course, that's not the expectation. Anything you get out of it, even if it is learning how to read some technical papers and learning how to judge whether an idea is good or not, whether a paper is good or not, that's helpful as
well. Yes, that is very true. I wish I know that when I just started college, but somehow I figured it out on my way, like growing up. But yes, that is very helpful suggestion. So let's move to our next question. This is also about future. I think what's a very interesting question is, what do you think are the promising area for future research in cloud computing? I know you talked about like how hardware and applications become diverse, and how it opens up a lot of opportunities. But this is a complicated problem. I'm just curious, like, what do you think it's the best way to deal with this kind of problems? Like from the operating system layer, from the hardware layer, from the drivers, like what do you think it's the most crucial way to solve this kind of problems and make the whole thing easier and more efficient?
Yeah, that's a good point. So I don't think there's a single layer where these kind of problems need to be addressed. In fact, the fact that we have so many layers of levels of indirection in the system stack is where a lot of the inefficiency comes from. There's a joke in architecture and systems, which is that you can solve every problem by adding another level of indirection, except for one, and it's having too many levels of indirection. And that's what happens in many cases. So I think the more where the systems are moving towards is looking across the system stack. You don't have to look across the entire system stack. Nobody can know everything about all the way from devices to how applications are built. But a lot of the opportunities for optimization come from looking at least across 2-3 layers of the system stack. So from hardware to the operating system, or from the middleware to how applications are designed, or between hardware and how applications are designed. It doesn't have to be everything, but a lot of the opportunities for gaining back the efficiency that you lose because of the end of Moore's law comes from looking across the system stack. So I think that's very promising. There's different ways of doing that. There's ways, so one way is by looking at hardware specialization, and there are several groups that are doing very interesting work on that. Another way is looking at how to automate a lot of the decisions in large-scale environments. One way is by applying ML, other ways are by applying analytical approaches or by making the system predictable so that you know how it will behave under different scenarios. There's different ways of doing it, but I think one very promising approach is looking at the interactions across the system stack.
The interactions across system layers.
Right.
So, there has been some discussions or I should say some concerns on these systems becomes more and more complicated. Like whenever you add a new hardware, people start to work on that hardware, like build specific compilers and write specific libraries, build specific operating systems on top of that. So would you think our systems are getting more and more complicated, and would you be worried about that?
Yeah, that's a good question. They definitely are getting more complicated. If you look at a data center 10 years ago, it was 100,000 copies of the same machine. And if you look at a data center today, it's 100,000 machines. They're not all unique, but there are several tens of different types of components. Not all of them are FPGAs and special purpose chips. Some of them are just different configurations of a server or different generations of a server. But even that type of heterogeneity complicates the system. So they're definitely becoming more heterogeneous and more complex. The question is, how do you abstract that from the user? So the user doesn't necessarily need to know what exactly hardware their application is running on, as long as you have a system in place that finds the right hardware for you. So that's one way of thinking about it. The other way is, how do you develop the right programming interfaces for this heterogeneous hardware so that all of its complexity, again, is not exposed to the user? And there's a lot of work in the community on how to make more programmable accelerators, again, whether they're FPGAs or ASICs. That's not something that I've looked at as much. We look more at how do you incorporate special purpose devices, special purpose hardware for system level tasks, not so much for end user applications, but there are a lot of groups that are looking at that.
I see. Well, that is a very interesting view. I know the programmability is not like the centric of your research, but that should also be something people think about. Okay, I think we're running out of time for this session. Let's go to the Q&A panel and see what people are curious about. So 1 second, let me pull up the questions. Okay, so on the top of the panel, someone asked, it's a career question. What's the most important thing you look for when you read someone's research statement? I think this is likely to be someone applying for graduate school or try to find a job. Right,
so it's good timing for this because the application. So the main thing I look at is research experience. Many times people focus too much on the GPA, and I'm not saying the GPA is not important, but it's more of a filter. So if the GPA is very low, then it's going to be an issue. But at least for me, when I review applications, a GPA of 3.8, 3.94, more than 4 doesn't make a lot of difference. What does make a difference is whether the student has some research experience and whether the recommendation letters talk about that research experience. So those are the main two things. It doesn't mean that you need to have a top tier conference paper or journal paper, depending on your area, but having a professor that can talk about a research project that you did and that you had some initiative in that research project and that is leading somewhere, even if there isn't a paper yet, that helps very much. So that's the main thing I would say.
So besides of like, I agree that research experience is very important. But when people go out and find a job or find a PhD position, they write research statement. So in the research statement, they talk about their past experience and maybe some future works. So what do you think is most important? What kind of research statement do you think is a good research statement that would wow, I want this guy?
Right. So it's the one that describes your research experience. Future work, just to be fully honest, is not that important in a research statement. I mean, it's good to know what field you want to work on, but you don't have to spend half the research statement saying that I'm going to work on this specific problem, because most likely you won't. Most likely you will work on something else. The most important thing is to describe your past research experience in a way that I can tell that you understood what the project was about and that you made some contributions to it, that it wasn't just a graduate student's project and you implemented a part of it. Yeah, it's okay. You don't have to implement the entire, or you don't have to build the entire project, but you need to understand what the scope of the project is, what are the main trade-offs, what were the main design questions, and what was accomplished. Then you can describe what part of it, was your focus. Those are the research statements that stand out. The ones where you can tell that the student understood what they were doing. They weren't just told by a graduate student to implement this, implement that, and so on.
I see. So I think this is the case when you review an undergrad's research statement when they apply for graduate school. Yeah. But how about when you submit a research statement when trying to find an academia job? Would that also have similar standard?
No, that's different. So what we want to see at that point is, first of all, that you can describe your past work, especially the papers or the projects that you led, but also future work is kind of important there. It's not the most important thing because, again, it's difficult to describe what you will do 5 years down the line. What we want to say is that for the next year or two, you have a couple of projects that you will start with. So you will be busy in the first couple of years until you figure out what is the main project that you will work on. So there, the future work serves to show what is your taste in selecting problems. And it's important. Again, it's not the thing that we put most weight on. Most weight on is put on how you describe your PhD work. What do you identify as your most important contribution? How do you describe, again, the trade-offs and the main design principles there? But also the future work matters more, definitely more than when you're applying from undergrad to grad school.
I see. So how about impact? Some people really care about their impact on the research impact on to the industry. Would that also be a factor you take into account?
Yeah, that's definitely helpful. So there's a couple of ways of showing that. One is you can put it in your research statement. So if there are, doesn't necessarily have to be industry, if there are academic groups that are using your work, if the work has received an award, if there are companies that are using the work, or if you've open sourced something and is widely used, that's something that you should definitely put in your research statement. What also helps is if you can get a recommendation letter, either from someone in the company that's using the work or from another group that has built upon your work and can testify that your work was indeed helpful. That helps as well, because that shows impact.
Thanks for those very helpful suggestions. I think we've spent enough time on this question. Let's move to the next one. So the next question is, what tips would you give to younger self with respect to diving into research? That's an interesting question.
What was the first part? I missed the first part.
What tips would you give to your younger self with respect to diving into research?
That's a good question. Let me think. Okay, so one thing I would do is I wouldn't as a first semester graduate student, I wouldn't start on a project of my own. I kind of went into the PhD having an idea of what I wanted to work on and started working on that. And, what I was saying before about my advisor being very supportive, that's definitely a positive thing. The negative thing of that is if you don't have someone to work with, it takes longer to complete something. And it's also harder when you get stuck on something, when you run into some roadblock, it's hard to get help. So if I was starting my PhD again, I think at least for the first semester or two, I would try to join an existing project, learn more about how research is done, how do you write a paper, how do you contribute to a large code base. And then from the second year on, I would start developing my own thing. It always depends how the project evolves, but that would be my approximate timeline. I think I would do that.
So it would be easier if you can know the way of doing research before actually doing them.
Sorry, say that again.
So it's a takeaway that it will be easier for you to do the research after you know the way of doing that.
Right, so it's easier to see how more senior graduate students work. Because when you see how somebody else works, you learn it yourself much faster than if you try to learn it on your own.
Yeah, that's very important. Yes. Okay, let's move to the next question. So what criteria, like, for example, publications, experience, or skills that institutions tend to look for in academia job market? How to set timelines to achieve that?
Right. So the main thing when reviewing faculty applications, the main thing, of course, is the research contributions. Now, sometimes people misunderstand that to mean that the people that have the most papers are the ones that will get the most faculty jobs. And that's not necessarily the case. Okay, I won't speak for all schools, but at least in the schools where I've reviewed applications, we pay more attention to the amount of impact that work that a PhD thesis had, as opposed to the quantity of publications that somebody has published, especially if they're not the first author in most of these publications. So in general, it's better to have one or two top tier papers where you're the first author and you are the right person to describe that work and present that work, and you can claim ownership over that work, instead of having 10 or 15 papers where you're only the first author in a couple and then you contributed in the rest, but they're not your main thing, and then it's hard to tell who contributed what where. So that is the main thing. Have one or two pieces of work where you are the lead contributor. And that can turn into your job talk, which is, when you get an interview in a university, you go and you give a talk, and then you have a series of meetings with the different faculty members. So you want to have one or two pieces of work that you can turn into that job talk. And there are no questions about whether that is your work or some other student's work or some collaborators' work. That's the main thing. The other thing is the recommendation letter. So that is similar to when applying for grad school. The main thing that we look at are the recommendation letters. So obviously your advisor will write you a good letter. If the letter from the advisor is not good, that's kind of a on the road. But you want some letters from people that you haven't necessarily worked with, but that know your work and can attest to the impact that it has had. This is what I was saying before, whether it's another group in academia that has used your work, whether it's someone from a company that is using your work, it helps a lot to say that, this project has had a lot of real world impact and it's being used in some large system or whatever. It has informed the design of something. That helps a lot. The research statement, it helps, so it needs to be well written. The teaching statements, it's there. It's not the main thing. It's good to have some experience. It's not the main thing that will make or break the job offer, but that's important as well.
I see. So on the research publications, I just want to ask a follow-up question on that one. So for the research publications, I'm not sure if you're aware of that, but I think many of the PhD students work in different areas, have different research topics during their PhDs. So do you think they should try to connect them and make a general topic for the job talk, or they should really dive into one of the most interesting topic and focus on that one during the job talk?
All right, so that will depend a lot on what the topics are. If it is nice to say that you have a story in your PhD, that you started from a problem and then that motivated another project and another and another. That's not always the case. I can tell you for myself, what I worked on in the first year and a half of my PhD wasn't really the topic of my PhD thesis. So I worked more on characterizing and generating cloud computing workloads, the storage activity and the network activity. And my PhD thesis topic is on scheduling and resource management. So, they're in the larger same area, but they're not the same topic. When the time came to give my job talk, I did not talk about that earlier project. First, because it wasn't the more impactful of the two, and also because you don't have to talk about everything. If you can always mention papers or projects that you worked on that are in a different area, but the job talk doesn't have to include everything. You have about 45 minutes for the job talk. Some of that is the introduction and the motivation on why your field of research is important. Some of that is future work. It takes, you have to keep in mind that this is a talk you give to the entire school or the entire department. It's not just people in your area. So you have to tell them why they should hire you, why your area is important. And that takes about 20 minutes. So you have really 20 to 25 minutes to talk about your work. You're not going to have the time to talk about everything. So you want to pick one or two projects, the most impactful ones, the ones that you got the best publications or whatever from, and talk about that.
So yes, I have also heard about this approach before, like you should focus on the most impactful work. But people have worked on other works as well, so it just seems a little bit wasteful to not mention them during the job talk.
So you can mention them. You can always have a summary slide, which is here are all my publications in all the different areas that I've worked on. And you can spin this to be a positive thing, which is I have experience in all these different areas, so I can collaborate with many different people. But you don't have to describe everything in detail. In fact, you won't have time to describe everything.
That's an interesting point. Knowing other areas can make collaboration easier. Okay, I think we have questions, or we have time for another question. So this question is, as a professor, how many different types of research directions do you feel you can balance at once in your research group? And how many feels like too many?
Right. So I think I'm a little bit different in that, in the sense that I like to work across different areas. This is not necessarily the most efficient thing to do because you have to learn a lot of different topics and that takes time. That comes down to what the students want to do as well. We have an overarching theme in the group, which is improving performance, efficiency, in some cases security of large-scale data centers. The specific projects within that can vary. So I have some students that are more on the electrical engineering side and they want to do more hardware projects, including hardware design, FPGAs, programmability of FPGAs and so on. And then I have students that are more on the CS side and want to do application design or programming framework design or scheduling, resource management. So it depends a lot on what the students want to do. Some students work on projects or on individual projects by themselves, and then some students work in small groups. I try to organize it in a way that even the students that work on individual projects have someone that they can reach out to on low-level technical details that knows enough about the area and can help them. Because, as a professor, you have to do a lot of things beyond working with the students. The most important is working with the students, but there's a lot of other things you have to do as well. And you don't always have the bandwidth to help everybody with low-level things. So I try to organize it in that way. It's an approximate job, so it doesn't always work that way. But as long as there is a unifying story, so you're not working on circuit design and then programming languages where there is no connection between the two, that is hard. There's some people that manage it, but that is hard. As long as you have some unifying theme across the different topics, that's fine.
I see. So as long as have a general topic for everyone in the group, that sounds fine.
Right.
So how do you think, like, if a student approaches you and proposes a topic that is not within your expertise, but it's close to the general topic that the group is actually working on, do you think that's a good idea to actually expand the group's expertise, or do you think the student should go to another advisor, maybe a better fit?
Right. Sometimes the answer is both. So I am happy to extend what we're working on in the group if there is an interesting problem. At the same time, it needs to be a problem where I can provide some advice. If it's something that I have no expertise on, even if I find it interesting, it's not fair for the student to work with me on that, because they won't be able to make enough progress as if they were working with someone that knows a lot about the field. What we do in such cases is co-advising. So if I do find the problem interesting, but there is somebody else in the department or the school that has more expertise, we can co-advise the student. And I find co-advising very beneficial because I learn more about a topic that I don't necessarily know a lot about. And it's very beneficial for the student as well, because they get different perspectives from two different people that come from different fields. Even if they don't come from different fields, they have different perspectives. So that's helpful too. And you have the bandwidth of two people instead of one, who maybe busy. So that's how we usually resolve that. There have been cases in my group where we did that. For example, some of the work that has more to do with hardware design, I wasn't as well versed in FPGA design, prototyping chips, and so on. So we are co-advising the student with somebody else who has much more expertise in that area, and that's working
well. That sounds very helpful. Okay, I think we are run out of time. So thanks very much for providing these on-the-fly questions. I know that. So this is about it for our current session. Thanks again, Christina, for joining us and providing so much helpful feedbacks and advices.
Thank you for having me.
Yes, thank you very much. So for the next sessions, we have a series of more guests for women in system panels. We have Minja and Irian. I think we will be announcing more details very soon. Probably we'll have the next session in September. So if you're interested, please check on our website, and we will send out follow-up emails as well. And you can also subscribe to our emails. So I think that's all for today. Thanks everyone to attend our session, and hope to see you again in the near future.
Thank you.
Okay, thank you.
Yeah, we have a question from the chat window. Where is the website? I guess this audience is asking what's the website of the system, the students at the system?
Yeah, I suppose, but he just
I'll paste this real quick.
Okay.
Let me get this. Oh wow, the audience has already dropped.
Yeah, I think he has dropped. Well, he will find us somewhere, I suppose.
Okay. Thank you.
Thank you. Have a good day.